Today we are going to continue our practical introduction to Python programming. Still on our first module, the basics, to talk about Python numbers. In this class, we're going to discuss more on integers and decimal numbers. To begin with, what are integers numbers? Integers are whole numbers with no decimal parts. Example, the number 1, -40, 7,000, etc. So in Python, integers are of the type int. Python integers have no size limit, they can be arbitrarily large, and there is no precision loss ever when you do integer arithmetic. On the other hand, what are decimal numbers in Python? Numbers with a fractional part such as 3.5, 2.0, and 1.01 are referred to as decimal numbers. These numbers can also be called floating point because the decimal point can float to any position in the number. Now, why are these numbers stored differently? Because computer chips are designed at the hardware level to handle integers and float using different circuits. Integers are stored as exact binary values, and floats are stored in three parts: sign, exponent, and the mantissa part. So these different designs actually allows floating point calculations to run very fast, and the trade-off is what? Is speed, which is gained by cutting off precision at a certain point. Talking about floating point precision, let's now switch to a Visual Studio Code where we can actually demonstrate using some expression to see how this precision is being handled by the Python interpreter. Now in my Visual Studio Code, I already have a Python file and a terminal open. All I need to do is type in the command Python as we saw earlier, and that activates my Python shell. I like to enlarge this so that we can actually have a good view. Talking about precision, Python float gives you approximately 15 to 17 significant digits of precision. And what this means is, if I type in the division expression such as 1 divided by 3, it gives us a result of 0.333, I think up to 16 significant digits of precision. So this is what this means. But beyond this, numbers are only approximated and not exact. But you need to know that this is a hardware limitation and not a Python limitation. Another example, when I type in a floating point or a decimal point number such as 1.0, so I'll make sure this exceeds 17 digits, maybe something like this. So when I run this, you can see Python rounds it up to 1.0. You can equally try some other floating point digits such as maybe this. Make sure it exceeds 17 digits. Python is actually going to round off this number to an exact number between 15 to 17 digits. So this is what we actually mean by this. Now we have what is called round off errors. You know, computer work in base 2, which is binary, right? Zeros and 1. While as human, we use base 10, which is decimal. Now, most decimal fractions cannot be represented exactly in binary, and this causes small errors called round-off error or floating point errors. Now, let me show you an example of a round-off error. Let me clear this terminal. So when I type in the division expression 7 divided by 3, so we have 2.3333 to 5. Mathematically, this should end in 3, but you can see it's now ending in 3, 5. So for most everyday programs, this doesn't matter, but there are some instances where you actually need to take note of errors like this. Another example of a round-off error can be adding two floating point numbers such as 0.1 plus 0.2. You can guess the result, right? 0.3. But let's see what will have the result here. So you can see instead of 0.3, we are now having even more precision in our result. So this is surprising, but actually it is correct. Now talking about round-off errors, when should we actually be concerned? When you are designing banking and finance programs, you need to take note of such errors because run-off errors on currency can accumulate. When you're also designing or working on scientific simulation, small errors can compound over calculations. Even as simple as equality comparisons, you shouldn't use a normal comparison operator such as the double equal to sign to compare floats directly. When you want to calculate or compare such number 0.1 plus 0.2 and you want to compare it to 0.3, which you are expecting to be the result, when you compare this, instead of having the output to be true, you have a false. Why? Because the calculation is rounding off to more than 3 precision, which you are actually expecting. So this is going to give you a false instead of a true. So you also need to take note of such errors. Now, this can actually be handled using built-in methods, but we're not going to talk about this right away. We're going to do that later. Now, let me clear my terminal. We can actually do what we call type checking in Python. Remember in our previous class, we said that everything in Python is an object. So, values are also objects. They are object of a specific class. More on that in our subsequent classes. For now, let's just check the types of values or even expression. Now, I can use the type function to check the type of values. If I pass in the argument 42 to the type function, it's going to return class int. That means 42 was a value is of the type int, which is an object of a specific class. Or I can also pass an expression 42 divided by 2 to the type function and it's going to return float. Why is it float? Because the result of 42 divided by 2 is a float, 21.0. So I can also type another expression 42. This time around, I'm going to use the integer division, which is a double slash divide by 2. And this time around, it's giving us type int. Why? Because the division operation 42 divided by 2, which is an integer division, gives us 21. Now, quickly, let's look at some of the integer and float arithmetic key differences. Clear my terminal. So the first one we have here is integer division. When you want to carry out an integer division, you use the double slash 7 double slash 2. So this is an example of an integer division. It's going to give you a 3. But using your true division, 7 divided by 2, is going to give you the exact precision of the operation, which is 0.5. So these are two different division operations. The first is an integer division, while the second is a true division as it's supposed to be. Now the next arithmetic operation we have is the modulo. We use the percent sign, 7 modulus 2. This is going to give you the remainder of your division, remainder 1. So the modulo operator actually gives you the remainder of a division operation. Now, quickly, let me use my type function. I can also do this, pass this expression to my type function, and it gives me the type of that division operation. So you can see this is an int. When I pass the true division, it gives me a float. When I pass the modulo 7 modulus 2, it gives me an int because the remainder is an integer. Now we also have mixed arithmetic. When you add an integer and a float, the result is always going to be a float. So this gives me 4.0. When you do 3.3 plus 1 or 2 rather, it also gives a float. So you need to know that any operation that involves two different types, integer and float, the result is always going to be a float. Talking about precision, what if you need accurate precision in your calculations? We have two modules that can actually handle this precision. We have the decimal module and we have the fraction module. So before you use this module, you will need to import them into your program. So how do we do this? Now back to our Python shell. So to use the decimal module, I'll need to import it from decimal, import decimal, and I also need to import the get context to use alongside the decimal function. Now I need to specify an exact precision value which I'll need to assign to the get context. I'm specifying that I need 50 exact precision added to my result. Let's define a result variable. So when I need to carry out a division operation such as 7 divided by 3, I don't assign this directly as a division. I need to pass it through the decimal function. So I'll pass my 7 divided by decimal 3. Now, when I print the result of this operation, which is stored in my result variable, you will see that an exact 50 precision is going to be added to the result operation. You can see. So my result now gives me 2.3 up to 50 digit precision, as you can see here. So I'll clear my terminal. For the fraction module, I can equally import the fraction module from fractions, import fraction. So I'm ready to use the fraction function. Now I can also define a result variable. So when I need to carry out a fraction operation such as 1 over 3 plus 1 over 6, I can actually pass those values to the fraction function. Fraction 1, you specify 1, and 3, that's 1 over 3 plus fraction, you pass the second operand, which is 1 over 6. So now I have that addition operation passed to the result. Now when I print this result to standard output, you can see we will have a fraction result. There you have it, 1 over 2. So you can leverage the decimal and the fraction module when you need exact precision. So this is going to be the end for this class.